I'm going to give a year update on Singularity again. I was here last year in the HPC Knowledge, and it's my pleasure to say that we accomplished some promises from last year, but in order to accomplish some promises, we converted a Singularity from that weird mixture of Python, Bash, like 2 or 3 lines in C++, and C, into a C Go project. So right now, Singularity is a 85% Go, 50% C project. If you are more interested, we have a full documentation on how we are playing around between Go and C. What really we are keeping of C is for maintaining all the security bits of the runtime and keeping the runtime secure, and just using Go to interface with external toolings, which I'm going to show why we are using Go now. We are following all Go standards from packaging to internals, so if you are a cloud native or a Go developer, it's really easy to just jump into the Singularity code base and start contributing. So this opened the door for Singularity, allowing people from this other ecosystem that is no HPC, but is the cloud native developers, and now they are contributing back to Singularity to integrate Singularity more into that ecosystem. Something that is really, like talking with Kenneth on the dependencies and whatnot, is that right now Singularity is carrying around all its dependencies in a vendor folder. So it's just a way of doing a Git clone, and you will have everything you need for building Singularity in there. And Singularity is being distributed as an RPM. Upcoming Debian, the 3.x series of Singularity is still not fully supported on Debian, but we are working on that. And we built our custom packaging tool called Make It. So we drop it at the auto tools for building Singularity, and we develop our own version called Make It, which is kind of auto tools, but it's just a lightweight auto tools for the needs that we have. What we win, what we lost when moving to Go. Right now, Singularity integrates really easy with Kubernetes, with Docker, and all the OCI ecosystem. All the cloud native tools are made in Go right now, so that was a big win. The concurrency model of Go is kind of tricky, but we are handling that with the C bits. So that's how we're playing with it. Go is really easy to learn and to develop, so thanks to Go, Singularity is winning open source contributors that they don't know much about C, and it's hard to contribute to a C code base, so now they can just contribute in the Go code base. And as I'm going to show, this opened the door for Singularity for container networking interfaces and other open source tooling that were out there that Singularity were lacking in its 2.x versions. Why Go? And I see that a lot of tools that have been presented since yesterday and today are made in Python. Again, all the ecosystem that we are moving on in the HPC is really made in Go, not in Python. All the APIs are being developed in Python, all the libraries and ways to interface with external tooling. Go test, this is my realm really. I work in the quality assurance and all the stability portion of Singularity. So all the tooling that Go brings into the table for doing unit testing and also integration testing, just out of the box when using Go is really interesting. And I can say now that the Singularity code base has something around 85% unit testing, so it's becoming a very stable project. And it's really easy to be productive in Go and having unit testing developed at the same time, so it is getting really fast to develop new features in Singularity right now. Now, moving away from the Go integration, this is a new feature. So this is a new feature that we are presenting in Singularity 3.x, which we call Singularity Container Format, or short SIF. Singularity image file. And as I was saying yesterday, kind of fast in the tutorial, from a high-level overview, it's kind of a tar file in steroids for containers, right? So we took all the good architectural designs from a tar file, and we optimized that for containers. So this is what you see in the big box is really a binary file that inside, by binary blocks, is containing the metadata of your container and also the file system of your container. And once you build that, it's read-only, right? So it gives you extra security for being read-only. And you can move and carry away this binary file as a tar file, right? So it becomes really easy to distribute, really easy to share, and easy to secure. So on the archival side, yesterday in the tutorial, we saw how by being a binary file, you can use regular old school PGP protocols on top to sign and verify this binary file. So if you can see here, we have a global header that is allowing us to store the architectural design, the architecture of the host that built that container. So if you go and read the binary file, it will tell you this container was built in a XYZ architecture at this time by this user. It really carries around a lot of good metadata of how the container was built and at what time, and the SHA-SUM of the whole binary file. The descriptors and the recipe definition, we saw the recipe definition, as I told yesterday in the tutorial. It became a good practice on storing how the container was built and the step-by-step that you used for creating that container. And the descriptors and the labels and environment is that metadata that you are carrying around with the container to tell the runtime how to run that container, right? So how are you going to play and interact with the file system? And an extra feature is the writable overlay. So after the signature block, you can add writable overlays that are not going to be signed, or they are not going to be verifiable, like trusted, but you can add extra data into that binary file after the signature block that we saw yesterday when doing the signing and verifying of the container. What's new in 3.0 and above? Singularity was lacking a lot of cloud integration, so we developed 3 main services to play along with Singularity. So right now, Singularity has its own registry that we call the container library, which is kind of a GitHub, Docker Hub fashion on which you can store by versions your container. So every container you upload into the library is going to be stored by the SHA-SUM. So even if you push the same container with a different tag, it is going to be stored with the same SHA-SUM. Or if you have a container with the same name and the same tag, but it has a different SHA-SUM, the library is going to be smart enough to store it in a different way. So it's really optimized for versioning the data. So it was designed thinking kind of on like in bioinformatics workflows or research workflows on which you need to really track down the version control of everything that you are doing. So the library is really designed for version control in your containers. The remote builder, as we saw yesterday, is really a cloud tool to allow users to build containers in a decoupled way from their host. So you can just run a remote build, close your laptop, go away, go home, and go back next day, and your container is going to be built for you in the cloud. And the key store service is a service that we created to store your PGP public keys so you can move around your container and then verify that it was the same container from one host to another. So I'm going to dive a little more into the features. So this is how the Singularity library looks. As I say, it is storing by tag, and also every block that you see is going to be a different SHA of the container. Okay. I got disconnected. I'm going to show it like this. So we saw yesterday the step of creating the token, and you can then interact with the library by using pull and push. As in Docker, you can use pull and push from the Docker registry, right? So this was a feature that all users were requesting on having a native integration of Singularity with a native registry. You can also run searches of specific names or tags of containers. So you can do Singularity search Ubuntu, and it is going to retrieve all the available Ubuntu versions that we have in the library. The remote builder. Wow, the definition is weird. If the video in were not playing wrong with me, so here you can type your own definition file. So let's say you don't want to use the CLI from the terminal. You can go into the web UI and paste your container definition here and click build. As we did yesterday in the tutorial by running Singularity build -- remote and pointing to the path of the definition. You can just copy and paste that definition, paste it here, and run. So it's thinking on non-terminal users and allowing these non-terminal users to build their containers from a web user interface. So we saw this yesterday, but this is from the terminal. But all that you can do in the terminal, you can also play it along in the web interface. And it is going to tell you here how your container build is going. If you click here in this link, it is going to point you to a streaming of the logs that are happening from the build. And if the build fails, this is going to behave as a CI fashion tool. So if it fails, it is going to show you the logs of why it failed. It is going to drop all the information of the container. There's no way of retrieving the container that it was being built when it fails, as you can do it in a local host. That's a trade-off. So without internet. The key service is like really plain. It's just a place to store your keys, and it is going to create a list of all the keys that you are uploading into your account. And you can play with that from the CLI like this. So you can create new pairs, see a list of all the key pairs that you have in your host. So you can have multiple key pairs in your host. As I was saying yesterday in the tutorial, you can have multiple signatures over one single container. So you can create like 3 different keys in your same host to say initial testing verified, right? So you can have 3 different signatures on top of the same container, some workflow like that. And this is what we are really proposing, is how you can sign your container, move it along with the library, and verify when pulling in a different host. Still without internet, which is kind of interesting. Network virtualization. So this is one of the big wins of moving into Go. Singularity adopted the container networking interface, which is part of the OCI environment. And right now, you can do all the fancy networking things. I'm not a network person, so this is like in a different language for me. But you can create DNS, different host names, specific internal networks in your system. All the fancy, I think I have internet again. All the fancy network virtualization that the cloud networking interface gives you as a user, now you can use and leverage that with Singularity. And now in some seconds, I'm going to show how are we using this in a native integrations with cloud native orchestrators. Security for the system admins and the people interested really in securing their workflows. Singularity 3.x also provides a lot of new security functionalities. You can add Linux kernel capabilities or drop capabilities from a specific container or from users. So you can create white list, black list of users of containers and say, this container when run, yeah, it can have specific capabilities, or when this user is running container, do not let this user to do these specific kernel capabilities. One of the main capabilities is allowing like set UID, right? So you can specify which containers are allowed to use set UID and which containers doesn't. And the bare example is ping, right? So you can say which container can run a ping to 8.8.8 or which containers cannot. So this really gives you a way to securing more your environment. You can keep privileges. So this is really think on people running Singularity inside Singularity for CI or testing purposes. So if you want to run Singularity inside Singularity, so use the full kernel capabilities, you just pass these keep privileges and you will have all the kernel privileges inside the container. Also, with the security flag, you can pass along a JSON or a full string defining how do you want to play with the, okay, I'm going to just make this. How do you want to play with the C Linux, the Armor obsec-conf. Here's an example of this command in this link on how can you create specific security definitions when running every container or for the users. C groups. In the HPC ecosystem, this is not of a big thing because we manage C groups via Slurm, via PBS, right? We let the C groups portion to the scheduler. But on the cloud native side, some of the orchestrators, they don't come with the C groups. They are expecting the container runtime to handle the C groups. So now with the Go integration, you can specify a sample like this and really contain the capabilities on hardware that your container has. So you can create containers with access to just one core or to access to a specific memory or to access to specific I/O or devices. So this is also a big win of moving into Go. Was moved, sorry. Runtime plugins. Singularity 3.2, I would say, in 3.1 was experimental. In 3.2, it introduced plugins, and now you can create different plugins, list your plugins, install them, make it available or uninstall them in your system. And we are already seeing a lot of use cases with these plugins. Last May, in the Singularity user group, we saw a lot of companies building already specific plugin containers on top of Singularity, and examples like that are plugins for I/O performance, I/O benchmarking. Also, we saw a user creating a plugin for system call monitoring, so you can create a plugin that every time you're running containers, it is going to tell you which system calls every container is running, things like that. So that's a big ecosystem now being created around the plugins. And we are now developing a plugin marketplace. So you can create a specific plugin and upload that as it were like a container registry, but a plugin registry. So this is kind of new, but we see a lot of people already jumping in developing plugins around containers. Development features. Singularity can now be installed in macOS. So this is the example. So you just download the PKG, click on it, and you have a Singularity running in your macOS via native integration with X-Hype, which is the native virtualization tool on a macOS. So you just go into the Sylabs webpage and look for the macOS link, and you have a Singularity running on macOS.
Is it still beta or is it stable now?
It's still beta because we are filing Sylabs as a development company into Apple, so we can have network capabilities. Right now, Singularity Desktop on macOS doesn't have network capabilities because some weird things on macOS that you need to be a verified company into Apple so you can run network capabilities. I don't know. But yeah, it's still beta. Now, big wins of moving into Go. I know some people here will not know about this. This is really cloud native, not into the HPC ecosystem. But right now, with the Singularity full in Go, and after Singularity 3.1, we became fully OCI compliant. You can run Singularity Kubernetes with Singularity underneath as a OCI container runtime via the Singularity CRI. This is open source, so if you go into the Sylabs GitHub repo, you can download the Singularity CRI tool, integrate with your Kubernetes, and start running a Kubernetes with Singularity runtime underneath. So this way you can just start running a Kubernetes cluster with rootless containers as Singularity and securing your Kubernetes deployment with SIF, and you can add all the sign-in and verification workflow into your Kubernetes ecosystem. But now going back to HPC, this is also open source now in the Sylabs repo. We developed a Kubernetes Slurm integration, and now we are opening this more with some development. We want to open this not just for Slurm, but for different schedulers. So the way we are proposing is that developers will interact with Kubernetes, and underneath, Kubernetes is going to orchestrate to different clusters. You can have clusters in specific sites with different schedulers, and Kubernetes is going to be able to ship your workloads into the schedulers. So this is when I say that we're bridging the gap between HPC and enterprise. Developers will just interact with Kubernetes. They don't need to know about Slurm or PDX or HT Condor. They will just request HPC jobs to Kubernetes, and Kubernetes underneath is going to be doing a meta scheduling into Slurm and deploying jobs into Slurm and retrieving back the information to the user as it were a Kubernetes deployment. Another big integration that we are playing in the cloud-native ecosystem is the Hashcode Nomad tool. So this is a cloud-native tool for high-throughput computing in the cloud. And right now you can also, this is open source, you can go into the Sylabs GitHub repo and download the Singularity plugin for Nomad and start running high-throughput computing in the cloud with the Hashcode tooling with Singularity tools. At the end of my talk, we're hiring. This is growing really fast and becoming really hard, like sustaining Slurm, Kubernetes, Nomad, whatnot. So we are hiring people interested in being half, like in the morning in HPC and in the afternoon in the cloud. So it's a really interesting company. You need to know about Slurm and you need to know about Kubernetes on the same day. And you can have meetings with Kubernetes and Slurm in the same meeting. So it's really interesting. That's my Twitter handle, and I'm open to questions. As I said, this was a really quick update on where are we with Singularity and Sylabs. Yesterday I was talking for 3 hours, so I don't want to talk for longer now.
Can you define cloud native?
Yeah, so when you say cloud native, it's tools that are designed since the beginning to be run in the cloud, right? And when I say cloud, I really mean APIs, right? So it's tools that are made to be interacting with other tools via REST, God forbid me, REST APIs, right? So you are developing your tool from scratch to interact with other tools via REST APIs. So that's when you take cloud native into the ground, is tools that interact with each other via APIs.
Oops. I guess I had another real question.
That's the boss.
The signing of the images, why isn't the header of the image signed to, like, I guess it seems like you can have all these signatures inside the image, but the header and the metadata aren't actually signed. So is that secure?
The whole binary is signed.
So in your diagram, right? Like, so if you go to your diagram of how...
The only thing that is not signed is what you do after signing.
Right. Which it doesn't... So, yeah. So, like, the signature, it looks like it only applies to the blue stuff, right? And so then, like...
Oh, no. The colors are really for describing that the global header is meta information on how you created the container. But really, what the signature block is doing is that it is storing the signature and telling that everything here up to there was signed with a PGP protocol.
Including the header? Okay. All right.
Well, the global header doesn't affect the runtime. It's a small JSON that tells you the architecture on which it was compiled, the date, and the OS on which it was compiled. It's like 4 or 5 items. It's not a big deal.
Okay.
Yeah, but everything that affects the behavior of the container is being signed. So it's the environment, the labels, the recipe, and the descriptor of how to run the container and how to play with the container.
I believe we still have time for another question. Okay. So thank you so much